and somewhere between like 5 and 5:10 to leave a bit of time for questions. Or so, like say like 5:10, 5:15. If there's a lot of questions in the middle, it's okay to go over. So it's not like a hard stop. But
That's awesome. Okay. Oh, can't read it. Press the key immediately to the right. Shift. Okay. Let's try to do something. Okay, cool. Awesome.
is it?
Yeah, it works. Yeah.
Is it Lakshmi-Narayanan?
Yes, that's right. Yeah. Balaji.
Are you ready?
Yeah, I'm ready. Yeah.
All right, so we're going to get started. So we're very pleased to be joined today by Balaji Lakshmi-Narayanan. He got his PhD with EYT at the Gatsby Institute in London and is now a research scientist at DeepMind. And he works on sort of connections between probability and uncertainty and deep learning, so trying to build good uncertainty estimates with deep learning models, building good generative models of data using neural networks, and he'll be talking today about uncertainty and out-of-distribution robustness.
Yeah, thank you. Thanks for the invitation. It's a pleasure to be here. And today I'm going to be talking about uncertainty and out-of-distribution robustness in deep learning. And this joint work with a lot of awesome colleagues at DeepMind, including Aki Matsukawa, Alex Britzel, Charles Blunder, Dylan Gurur, Eric Nelisnik, and EYT. Okay, so the way I'm going to do it is I'll give initially like a bit of background, and then I'll talk about like a few papers I've worked on, and then when I switch gears to the second part of the talk, I'll also give like a somewhat of a background on generative models at that point. So feel free to interrupt if anything is unclear. Yeah. Okay. So the big question we are interested in is quantifying uncertainty in deep learning, and in particular, we are interested in predictive uncertainty. And what do I mean by that? First, why do we care about predictive uncertainty? It's because we are using deep learning models to make lots of predictions in the real world, and if you have good uncertainty scores, they can quantify when we can trust the model's predictions. And this is very useful to decide when do we use this model, when do we trust this model or not. And what do I mean by that? Typically what it means is you output some kind of like distribution over the outputs rather than a point estimate. And for example, for classification, this could mean that rather than predicting just like a class label, you also predict a confidence with which you believe that to be the class label. Or in the multi-label setting, maybe you output a distribution over the classes themselves. And in regression, what it means is rather than just outputting like a point value, you output like say a mean and a variance. So this is like the simplest example, but there's a lot more sophisticated things that you can do here. And where does this uncertainty come from? Basically, there are two sources in some sense in modeling problems. So the first is the inherent stochasticity in whatever we are trying to model itself. So we are trying to model, so imagine you're doing supervised learning where you're trying to predict some y given some x. And there could be inherent stochasticity in the y itself. So an example could be you're trying to model like the winning odds in a casino, or say you're trying to model some kind of like y target that has been measured with some kind of like measurement noise, and maybe there is some noise in the labeling process. You're trying to you have some images and the labels come from some human annotators, and the outcome could depend on who you ask, and there's some inherent stochasticity in that itself. And this is what is typically known as aleatoric uncertainty. And a useful way to remember this is it's considered to be typically irreducible uncertainty in the sense that given these set of features x, there is no way to reduce this inherent stochasticity itself. And this uncertainty also persists in the limit of infinite data. So you cannot reduce this by collecting a lot more data. You can presumably collect it, reduce this through maybe like getting more views or more features or anything like that, but not through like IID samples. Like more samples in N may not actually solve this problem. And the second source of uncertainty is what we typically call as model uncertainty, and this is to do with the fact that we are using really big models with lots of parameters, and the training data, there could be multiple values of parameters which are consistent with the training data. So here's like a simple example where, I don't know how well you can see it, but I have data points from two classes, and you're trying to model like a classifier surface, and you can already see that there are tons of classifiers values which are consistent, which can perfectly explain all the training data. So given training data, there's not a single value of theta which perfectly fits these, so there are multiple values consistent. So there is a model uncertainty itself. So at test time, which one of these do you use? You may not want to pick maybe just one of them. You want to pick all of them, or kind of like weight them in some interesting ways, and there are all kinds of things you can do here. And this is what is called as epistemic uncertainty in the literature. And this is considered to be reducible uncertainty, because you can imagine that maybe if you observe like more training points in this region and this region and this region, at some point you may, depending on how big the dimensionality of your data is, at some point it may be constrained enough that there will be just like one or up to some limits of identifiability, just one set of parameters which perfectly explains your data. So maybe even if your data was generated by some theta star, which is in this hypothesis space, then in the limit of infinite data, your estimator would kind of converge to this theta basically. And this is considered, the distinction between this and the previous is that this goes down as you collect, this does not go down as you collect more data. This goes down, it's reducible, so it goes down as you collect more data. So that's a key difference. Before jumping on, I will also motivate by lots of applications, and there are lots of applications where we care about like predictive uncertainty. And for this talk, uncertainty is a huge topic. It touches on almost all aspects of machine learning. So this is not an exhaustive list by any means. And I'm even just focusing on only on predictive uncertainty. There's also cases where weight uncertainty matters. Like for instance, if you're interested in like compression or doing some kind of like sensitivity analysis to figure out like which part of your features affect the output like a lot more or things like this. But even with predictive uncertainty, there are lots of interesting applications. So the most important one is some kind of like decision making. When you're making some prediction, we have models making all these predictions, but ultimately we want to use them for some kind of like decision making. And there, the cost of making the decision, you kind of need to think about what is the optimal cost in terms of like decisions, or maybe even in the binary classification, you want to think about like false positives, false negatives, and whatnot. And this is very important in like healthcare or other applications where the relative costs of those may be very different. So imagine you're trying to predict some kind of like doing some kind of like diagnosis that looks up some scan and trying to predict something. And here is a very important, you need some kind of like confidence to make sure that you're to act correctly in the world. And also one other thing is active learning, and this comes up all the time. So maybe you want to collect more data and you want to use the uncertainty to hopefully kind of collect data in the region which would maximally, so that you learn the most, you make the most efficient use of your data collection pipeline. And another example is dealing with noisy data in the training set, maybe like measurement noise or things like this. You want to make sure your modeling is robust to those. And also another big thing that comes in a lot of real world systems is train test queue. So your training data was collected according to some procedure, but the test data might drift, and you want to make sure that the model's predictions are still valid, or you can still rely on the model's predictions when the test comes from a different distribution. And reinforcement learning is another big area, and there's like things around uncertainty is at the heart of exploration, and it also comes up in a lot of like cases where we care about like safe exploration and things like this. There's also stuff around like model interpretability and visualization. If you want to understand the model, you want to kind of like visualize where the classification boundaries are and where the model is like least confident and things like this. So this comes up there as well. And in general, I think like if you care about applying machine learning in the real world, then you want to kind of like build modular systems. And if you can quantify confidence there, if they know what they don't know, then you can chain them together somehow, and that would be a great having some kind of like confidence measure will allow you to chain these systems together. And there are many more applications. Yeah.
So I guess the active learning application one is interesting, because that seems like one where the difference between epistemic and aleatoric uncertainty is very important.
Yes.
Like if I understand correctly, one of the ways people do active learning is they try to sample the data points that are most uncertain. But if that's like inherent noise in the data, it seems like that wouldn't be very good.
Yeah, so there's also stuff around like things where information maximization and things like this. People ask like questions like, what is the expected improvement if I label this point, or things like this. So that's where that would be able to distinguish between these two sources of uncertainty. Yeah, yeah.
Okay, so this would be a different criterion.
That would be a different criterion. Yeah, but in general, I'll come back to that point. But in general, if you don't know anything about your problem, distinguish between these two sources of aleatoric and epistemic uncertainty is difficult. And then as a practitioner, you would try to add as many features as possible to reduce the inherent uncertainty, because you don't want, maybe you want to add as many features as possible to kind of, so that you have all the features to kind of like predict that, right? Like so, and this is like a modeling choice in some sense, but it may not be always possible to perfectly separate the two. It's useful to know that these distinctions exist, but when you are modeling, there are a lot of other choices which will become interesting. Yeah. All right. So let's move on. So before I go on to like methodology, I think it's useful to understand how do we measure uncertainty. This is one of the things that comes up a lot in practice. What is like good uncertainty measure kind of like look like? And there are typically two measures that people care about. So the first is what is called calibration, and this really measures. So what it's trying to measure is the system is making some subjective forecast and assigning a particular probability to some events, right? So how well does this actually align with what happens in the real world? And one motivating example is a use case used in the weather forecasting literature, where imagine you're trying to predict. There's a 50% probability that it will rain today, and you have these predictions made for a whole series of days, and maybe you assign 50% probability for one day, 70% probability for another day, 90% and whatnot. And what you do is, of all the days you assigned 80% probability of rain, on what fraction of the days did it actually rain? If it rained 80% of those days, then your subjective belief about the world is aligned with what the frequentist, whatever happened in the frequentist average. So it means that you're well calibrated. And this is, there are a lot of measures people can do. So one common way is kind of like do calibration curve, which basically does exactly what I mentioned, except that you take the probability from 0 to 1, you kind of like bin it up, and you kind of like look at what happens on cases where I said between 0 to 10, what fraction it actually rained. On cases where I predicted something between 10 to 20, what fraction did it rain, and things like this. You sketch out the entire curve, and you can also compute some summary statistics, kind of like expected calibration error, which is kind of like an ideal calibrator thing, should be close to the diagonal, because your subjective forecast should match the empirical frequency, and you can compute some kind of like deviation from the diagonal in some sense. The other part that we kind of care about goes back to what I was talking about, like dataset shift, which is does the system exhibit higher uncertainty on inputs far away from training data? And this comes up a lot if you have read about like Gaussian processes and things like this. This is one of the appeals of those methods. So they naturally reduce their uncertainty close to the training data and exhibit higher uncertainty as you move further away. And this would be a very useful practice, because you can imagine that the model, so imagine you're training some kind of like conditional predictor P of y given x, and this has only seen x in cases where x comes from some p train of x. But when you show some x which is very far away from p train, the model has not seen enough examples, so it may generalize in unintentional ways. So you may not want to trust the model's predictions in those regions. So the places where the inputs that are far away from the training data, or what is known as out of distribution inputs, or OOD for short, you'll see and we typically expect things to exhibit higher uncertainty as you move further away from training data. And there is no agreed upon measure, I would say, but there are a couple of things that people commonly use. So one is you need to measure some kind of like the model's ability to reject like unseen inputs. And one way people can do it is if you want to test the model's robustness to unseen inputs, it's very clear that just cross-validation is not sufficient, right? Like, so if you just do train and test, even though they are out of sample in some sense, the test distribution, it comes from the same IID distribution as the training. So if you measure performance on that, that can significantly overestimate how accurate your model is, and you want to kind of like measure something on a completely different data set. So maybe if you're trained on MNIST, you're trained on a completely different data set. Like a human would say this is not at all MNIST, and you see how the model gives predictions there. I'll describe this in more detail as we go further. So, and one of the challenges in uncertainty is actually the lack of ground truth. In many applications, we don't really have the ground truth because we are trying to model some P of y given x, but in practice, we may just observe one sample from this conditional distribution in some cases, and we may not observe the entire distribution. So that makes it also kind of like challenging, and in some cases, even the right answer is kind of like hard to define. And there are some places where the community may agree on what is the right target to measure against, but in other cases, it may be less clear. Like you can imagine there's a whole spectrum between like out of distribution and your out of sample, and somewhere as you get closer to the out of sample, there may be some points where it's not clear like what is the right thing to expect from the model. And also I talked about like the real motivating use case of a lot of these uncertainty based research is applications where there is some decision making involved, and it may be hard to model the choice of the decisions, the cost of the decisions properly when you do the trainings. In some cases, it's kind of like easy. If it's like binary classification or something, it's fine. But in other cases, it's hard to pinpoint, tie back like the metric to exactly the quality of uncertainty because of other potential confounding factors and whatnot in your experimentation. So, okay, so far I've talked about something more general than just deep networks. So it's worthwhile kind of like taking a step back and thinking, okay, there are all these interesting problems around like uncertainty and things like this. Is it even like a problem for deep nets? That's the first question worth asking. And the answer is yes, it is a problem. And I'll give you like two examples. The first is to show that, remember I was talking about like these two metrics. One is calibration, and there is this paper, really nice paper, which shows that deep networks are very poorly calibrated. And this plot describes the calibration curve that I was kind of like talking about before. So I'll just focus on this plot for now. And this is what is called a probability calibration curve. You may also hear the term reliability diagram, and it basically refers to this one. And what it shows is you take the confidence of the prediction, which is the max value of your softmax, and then you bin it. So the probability is a value between 0 to 1. You take values from 0 to 0.1, you bin it, 0.1 to 0.2, and so on, and you actually measure the fraction of times it was accurate. So a perfectly calibrated model would lie on the diagonal of this, and the red measures the gap. And this show on the left you have the output for like a small network, and on the right you have this gap for a deep network. And you can see that for a deep network, this gap is so huge, which shows that the deep networks tend to be very poorly calibrated. And going back to the next part, which is about like out of distribution robustness, there is this another really nice paper which shows that deep networks tend to assign very high confidence predictions to like what a human would say this is like none of the above, but deep networks tend to assign very high confidence. Yes?
So for that previous paper, like one result I remember from there is that if you just kind of like anneal the probabilities, that it becomes well calibrated. like, do you think that, like, in your mind, is that basically the solution, or should we be like happy with that or unhappy with it?
So I think that's one solution, but I think there's it's measuring. It solves for classification problems. Like it already what this paper showed was if you do temperature scaling to the logits, it already gives you like calibration, but it's unclear whether this would translate to like out of distribution robustness, for instance. That part is unclear, right? Like, so there's a lot of questions I think we haven't fully understood. Yeah. So, but this is definitely better than not doing that, at least on like a lot. If you're training a classifier, you should absolutely do it. Yeah. Yeah. So, and this paper also showed that deep networks tend to assign like high confidence predictions to like unrecognizable images. And why does this happen? Like the human would look at this, and if you trained a classifier on, I don't know if it was ImageNet, it's probably ImageNet, they would say it doesn't look like any of the ImageNet classes. But why doesn't a deep network? Deep networks not only make mistakes, but they are very overconfident when they make these mistakes, and it's a bad thing. Yeah. Okay. So I'll give you a quick overview of like Bayesian deep learning because it's the dominant framework for addressing a lot of these questions around like uncertainty and better uncertainty quantification in deep nets. So, okay, Bayesian model averaging in a nutshell. So the high level idea is the following. So you start off with some prior over parameters, which is some kind of like distribution over P of theta, and then you compute the posterior distribution. I'm trying to be as agnostic to the model as possible so that you get the high level idea, but I'll walk through some of the things later. So you compute a posterior distribution given, so maybe initially you assumed some kind of like Gaussian prior over your parameters, but then maybe after you observe the data, there's only like a few of the values are actually consistent with the observed data. So you can imagine that after observing, if you go back to the first plot that I was kind of trying to show you, if you have these two classes in the classification, after you observe the data, it already rules out like a lot of combinations of weights, and it concentrates. It's not all possible weights, but only the subset of weights which are kind of like consistent with the data, and you kind of like compute the probability with which how well they explain the data. That's what your posterior is measuring. And at test time, you translate parameter uncertainty to predictive uncertainty. And what does that mean? What you do is, instead of using like a single value of theta to predict, you sample multiple parameters from your posterior distribution, and then you compute your predictions and combine those predictions in some way. So maybe if each of the individual networks is outputting some kind of like probability, you average the probabilities. That could be like one way to do it. And the challenge is that the true posterior distribution tends to be multimodal and very hard to compute in like high dimensions, and there are two dominant solutions for solving that. One is variational inference, where you approximate the posterior distribution by a simpler parametric distribution, so maybe like a Gaussian, like Q of theta or something like that. And because it's parametric and simple, it usually cannot capture all aspects of P theta, the true posterior, and if you imagine like your true posterior is like some kind of like mixture of Gaussians, this may just capture like one of the modes because it's restricted in capacity. And some examples of this are Laplace approximation, which is basically making a Gaussian approximation to your posterior. And there's also variational inference methods like Bayes by backprop or dropout variational inference and things like this. The other class of methods is Markov chain Monte Carlo based methods, which do not make a parametric assumption, which is good. Unlike variational inference, they don't make parametric assumption. What they do is they define a Markov chain that eventually samples from the true posterior. But the big challenge is a lot of these methods, whatever works for like low dimensions, like Hamiltonian Monte Carlo and variance, work really well on like low dimensional problems. But a big challenge has been like combining them with like stochastic gradient methods and making them work for like deep networks where the structure of the geometry is kind of like unknown and things like this. And there's a lot of recent work on stochastic gradient MCMC, such as like you may have heard about stochastic gradient Langevin dynamics, stochastic versions of HMC and other MCMC, stochastic gradient MCMC methods. But it's still pretty much work in progress. The community has made a lot of progress, but still it's a challenging problem. And it's also worthwhile asking, why Bayesian deep learning? Why is this the most popular paradigm, right? Like, so the answer is, you may hear, when you read papers, you may hear things like Bayesian inference offers a principal solution to this problem. In what sense is it principal? It's worth understanding that as well. And the argument typically goes as follows. So Bayesian model averaging satisfies the axioms of probability because it uses Bayes rule. So given some, so if you imagine, if you look here, we had some p of theta, and given some data, we compute p of theta given d using Bayes rule, right? So you satisfy the axioms of probability, and there is some, it's well known that if you don't satisfy the axioms of probability, you can always find a better rule. Or like a more optimal rule, and this is what is called the Dutch book argument in some sense. So in some sense, you can show that if you can compute the true posterior, then Bayesian model averaging is optimal. So what this argument basically says is that Bayesian model averaging is the optimal thing to do if you believe that your prior is correct. That is, what does it mean? It means that your true model, the one that generated the data, some theta star, is within like your hypothesis class. This is usually not a big, as strong an assumption in this, for deep nets at least, because we know that as long as you choose like the right architecture and things like this, you can appeal to the universal approximation theorem that it's a very powerful function approximator in some cases. Yeah.
And don't you need more than that? Like, don't you need the model to be randomly sampled from within your hypothesis class according to the prior?
Yes, that's also I think if it is I think as long as it's identifiable and within the hypothesis class, I think it should be okay, but maybe there's something that I'm missing. Maybe let's discuss offline. Yeah, yeah. But the more important assumption is that the true posterior can be computed exactly. I think this is a more challenging thing to do in practice. So it's a great thing. Bayesian deep learning is gaining a lot of popularity, and there's a lot of great tools. If you, depending on your problem domain, if you're interested in, like, if you care about uncertainty in some application, if your number of data points, if the dimensionality of your data is actually less, then there are pretty good tools for dealing with these things, like Hamiltonian Monte Carlo or Gaussian process and things like this. And there's also better software and probabilistic programming tools. The real challenge is in like really deep networks with millions of parameters and multimodal posteriors. We don't have great tools in that regime, and that's the more challenging part of the current. That's a challenge for current research. Okay, so given this, is there, you may wonder, like, what is a scalable alternative to Bayesian model averaging for quantifying predictive uncertainty, right? So the answer is there does exist a scalable alternative, and I'm going to talk about that next. And this is based on this paper, which is joint work with Alex Pretzel and Charles Blunder. And the idea is actually quite simple. And if you have followed the narrative so far, it should obviously kind of be like obvious in hindsight, hopefully. So what we did with this paper was, at that time, our goal was Bayesian methods are great, but we need like a really strong non-Bayesian baseline to actually measure how much benefit we are getting out of the Bayesianness, and what's a really good non-Bayesian baseline, right? So what we are going for was a probabilistic but a non-Bayesian baseline, so that we can actually measure how does this compare against like state-of-the-art Bayesian deep learning. And we show that it performs well on the evaluation metrics, which I'll talk about in a bit. And we also wanted something that's really simple to implement. So the overhead on top of like training a deep network with Adam or something should be somewhat minimal, and it will also be scalable to like large data sets such as ImageNet. So and also robust. Some of the methods, like variational inference methods and like expectation propagation and things like this, make some assumptions about the network, and it's kind of like a pain to implement them from scratch for every architecture. So you want something that's more like a wrapper method around and works robustly across many types of output types as well as architectures and things like this. So here's a simple recipe for uncertainty estimation. So the first is you let the neural network parameterize a distribution. In classification, we already do this because in network outputs a softmax distribution, right? Like, so which is a probability distribution. But in regression, we typically still the dominant way is to let the neural network output a scalar value, and here we make sure that the neural network always outputs a distribution. And in the simplest case, the network outputs a Gaussian with mean mu and variance theta, and it's very easy to implement because you just take your vanilla neural network that was predicting a scalar and you add like a variance component. You add like an additional head that predicts the variance as well. And then for training, you make sure you use a proper scoring rule as a training criterion. And typically the one we do for maximum likelihood, it's a proper scoring rule because the log is a proper scoring rule. For classification, the cross entropy loss that we typically use happens to be a proper scoring rule. For regression, if you use mean square error, it's not a proper scoring rule, so you have to use a Gaussian likelihood given this mean and variance. And at that time, we did this more than 3 years ago, actually now. So at that time, this benefit was not known, but what we found was adding like adversarial training was a simple and effective way to smooth. So the way so we did something, the simplest thing, which is the fast sign gradient method. And what you do is you augment your training data with some x plus delta x, where this delta x is chosen so you go in the direction which minimizes your log likelihood, and then you take a signed vector so that it's within like an epsilon ball of your original input. And what it does under the hood, you can show that this encourages p of y given x to be very similar to p of y given x plus delta x. And you can imagine that Bayesian averaging, when you average predictions through a lot of weights, you get like a smooth vector, and this is a simple way to kind of like smooth your predictions p of y given x so that it's locally smooth. This is optional, it's not always necessary. The more important ingredient is you train an ensemble of M networks with random initialization. In this case, you could also use the bootstrap, but in our experiments, we just took we gave the entire data set to all the individual networks and just random initialization. And then at test time, what you do is each network outputs a distribution because each network parameterizes a distribution. So you get a distribution predicted from each of the inputs, and then you treat it as kind of like a mixture model. So p of y given x happens to be, you combine the predictions, you treat it as a mixture model, right? So this is pretty simple, and by design we kept it as simple as possible and as minimal overhead. Let's see how well this does, right? And note that if you think about this, at first glance it looks kind of awfully similar to what I was talking about before with like Bayesian model averaging, right? But it turns out it's actually doing something different, and the distinction is kind of interesting to think about. Here we are combining models, treating them like uniform weights here, whereas Bayesian model averaging weights each of these thetas by the posterior probability, and that's what Bayesian model averaging does, whereas we are doing model combination where we are treating all the models as equal and combining them. And the difference is explained by this illustration. This is a very short note. I definitely encourage you to go and read this short paper, just literally titled Bayesian model averaging is not model combination. And I don't have time to go into the details, but the high level story is that Bayesian model averaging does soft model selection. And in the limit of infinite data, assuming that your model class is identifiable, BMA converges to a single model. It peaks around like the right theta star, whereas ensembles do model combination, and the hypothesis space is fundamentally quite different, even though computationally they look kind of like similar. You could do Bayesian model averaging on the hypothesis, on a bigger hypothesis space as well, but let's leave it for that. Yeah. So, okay, going back to the method, so how well does this do? So here's a simple regression task that's commonly used in a lot of papers on uncertainty. So the true function is the blue line. I think it's y is equal to x cubed, if I'm not mistaken. And the red points are the training data, which are drawn from this blue curve with a little bit of noise. And in the left plot, what I'm showing is a non-probabilistic network. What happens if you train using mean square error? And you just train like 5 networks, trained using mean square error, and you use the empirical variance between them as a measure of uncertainty. And you can already see that as you move further away from the training data, this significantly underestimates. So here you can see that it completely misses the blue line, right? Like, so it's very overconfident. So it significantly underestimates the true uncertainty. And in the middle, what I'm showing is a single probabilistic network. So remember I was telling you about using a single network, but making sure it predicts a distribution. And even if you use a single network, it already does a much better job. And this is much easier to train, right? Because all you're really doing is just adding an additional head to the output and then changing the loss with which you train your network. You can use any kind of like deep network that you want. And this already achieves pretty good uncertainty. And on the right, what I show is if you train 5 such networks, which are randomly initialized, and then you average them, you already get pretty good uncertainty bands. So this is really simple to implement and works well on this toy example. And I won't go into these details, but we also compare to like a popular benchmark for a lot of like regression problems from UCI regression. And the key, we compare root mean square error, which measures how accurate the mean prediction is, as well as negative log likelihood, which measures uncertainty. And you can see that our method is, at that time, we compared to whatever was state of the art, which was probabilistic backprop and Monte Carlo dropout. And it achieves better negative log likelihood, slightly worse RMSE. And it's completely non-Bayesian, but it's still within the ballpark of these more like better methods, which you believe should be much better according to the theory, right? It's an interesting result. And one plot which is kind of like interesting, going back, you can do like a version of the calibration curve that I mentioned, and you can see that if you train, so you expect the diagonal is what you kind of like expect, and if you use a non-probabilistic network and use the empirical variance, this is the result you get. So basically, in cases where the model thought it was 80% confident, the actual value was maybe only there in 20% of the time or something. So here it's very clear that these networks are very overconfident. So anything below the diagonal line means you're overconfident. Our model achieves kind of like this. It's slightly underconfident, but if you're the perfect thing is to be on the diagonal. But in many applications, it's better to be underconfident than, because you'd err on the side of caution than do some rash decision or something like that. Okay, and I talked about like regression results. We also tried some classification experiments, and this is like a simple example on MNIST using like MLPs. I think we used a 3-layer MLP, and on the x-axis, I'm plotting. On the x-axis is the number of networks, and the y-axis, the leftmost plot is the classification error, and the other two, which does not, it's a classification error, we care about it, but it does not capture uncertainty. The negative log likelihood and Bayes score capture uncertainty. In all cases, lower value is better, and as you can see, so the blue is our method, ensemble plus adversarial training, and these are all like ensemble variance, and the green line is Monte Carlo dropout. And here you can see that ensembles lead to better predictive uncertainty. And as you can increase the number of networks from 1 to, I think we went all the way to 15. 1 to 15, you can see that all metrics start improving dramatically. And so we did some ablation experiments with variants of our method, and you can see that ensemble augmented with adversarial training does much better than without adversarial training, so which is also good to see. And we have similar, and all of these are much better than Monte Carlo dropout. And we have similar results on SVHN using convolutional neural nets instead of MLPs. Okay. We also show results in the paper on ImageNet, and the trends are kind of similar.
Are the axes swapped for the first and second figures? I'm just trying to figure out, like, it seems like classification errors should be around 3% and negative a lot likely it should be around 1 rather than the other way around.
This one, you mean?
Yeah, or like classification error should be between 0 and 1, right? So how could it be?
Oh, it's percentage.
Oh, that's
yeah,
percent.
yeah. Sorry,
Okay,
yeah, it's percentage.
Okay,
Yeah,
cool.
yeah.
Okay, that makes a lot more sense.
Yeah.
Okay.
Sorry, I should have been clear. Yeah. Yeah. So this is a result, and the next thing we kind of like checked at that time was we wanted to evaluate how well this predictive uncertainty is on OOD, and if you remember all of these tests so far, we do some train test split, and they are still from the same IID distribution. So we want to measure how well it performs on something OOD. That's a more interesting, more realistic test. Yeah.
So is this training against Breyer score, or?
So this is all trained using cross entropy.
Okay.
Yeah.
I guess my question is, so Breyer score is, like a binary classification score. Is there a way to like use this sort of result like ensembling? I mean, like predict random networks, like uncertainty-aware networks, to think about which classes are confused more often?
Yeah, we didn't do it here, but you can do that as well. I think if you had some kind of like, you can do something like hierarchical softmax, which would internally kind of like weight the different classes or something, or maybe if you had some kind of like structure in the class label. So maybe if you're predicting, I don't know, like you're doing like ordinal regression or something where you're trying to predict age or something, where the mistaking 3 for 2 is much better than like 3 to 100, say. There's some structure, right? Like, so there you can use other losses. Yeah.
Okay, so that would be training against something besides crossing.
Yes, yeah. But here we are not doing that. Yeah. All right. So the next is goes to this thing about like OOD that I was talking about, and what we do was we take the exact same networks, we train them on MNIST, and then we evaluate on this known test set, which measures out of sample generalization in some sense, and we also measure how it predicts on an unknown test set. Like, and this data set we picked it mainly because it was literally called not MNIST, which makes it easy to say. It's like not MNIST, and this contains 28 by 28 characters instead of digits. So a human looking at it would go, well, this looks like an A and not like anything between 0 to 9. And in the paper, you can also see we train like other kinds of like variants where you train on SVHN, test on CFAR, and train on like subsets of ImageNet. It turns out like ImageNet has maybe like 100 out of the 1,000, like 100 categories of dogs. So we can like train on all the dog categories. And at test time, we show like images of cars and other things, which is never seen during training. And I'll just talk about one set of results, and the overall trends are very similar. So what we did is, like I said, the train is MNIST. Test we have MNIST as well as a not MNIST, which is completely OOD. And what we see on the left is what are the results when you evaluate on test MNIST, right? So as a measure of uncertainty, we are using predictive entropy, which is so the closer it is to uniform, it will become more, the entropy will increase, but the lower here it's a known test set, so the model can, MNIST is pretty simple, so the model can really predict with very high confidence, and the entropy is very low, as you would expect. And changing the number of networks in the ensemble does not really make a difference. But as you vary, so this is prediction, the entropy, but computed on not MNIST. So here you can see something interesting. So I'll first talk about this plot, which is variance of ensemble, where you vary the ensemble size from 1 to 5 to 10. And you can see that if you use a single network, it's actually very confident, even when it predicts on not MNIST, which it should say maybe like you would expect it to output like a uniform probability or something. But it actually, when it outputs some prediction, it's very high confidence. And whereas if you use, as you increase ensemble size, the entropy increases drastically, which is a good thing. And when we compare to like Monte Carlo dropout, so here you can see that even if you increase, this is this gives some robustness, but not as much as like ensembles, which are much better. And another way to kind of see that result, just motivated by a practical application, is one way to use the system is the following. So you only trust the system when you take the confidence that it reports, and then you only evaluate the cases where the confidence is greater than some threshold tau. And if it says I don't know, you don't penalize the model. In the ideal case, there is some cost, but for now, assume that it's okay for the model to say I don't know, and you only measure the confidence on the case where only measure the accuracy on the case where the model is say more than 90% confident, right? Like so, this is the exact same setup as before and the exact same result. I'm just plotting it in a slightly different way, and this is what the results look like. So on the x-axis, we have the confidence threshold, and on the y-axis, we have the accuracy. So intuitively, what we expect is, as the model becomes more confident, the accuracy should go up a lot, and that does happen for all of the methods. You can see that for ensemble variants, they actually go up much better than say Monte Carlo dropout. And here, what this really says is, in the case where the model is more than 90% confident, it was only accurate 50% of the time, right? Like so, overconfidence and being wrong is a bad combination usually in practice. So, and this is much more robust in that case. So this is like a useful plot to measure, diagnose the ability of your model to react to like OOD inputs. Yeah.
Do you have any intuition for why it bottoms out at 33%?
Oh, the reason is basically the not MNIST test set is twice as big as the MNIST test set. So I always say it's wrong if it's basically the way I computed this. It's an artifact of the way I computed it. So I just if I set the threshold to 0, I force the model to make a prediction, and by construction, anything that predicts on not MNIST, it would make a mistake, right? If it makes a prediction, it has never seen that example before, so that's why it bottoms out there. Yeah, and we have similar results on other data sets as well. And you can also, I'm going to skip this slide, but taking a step back, I spoke a lot about like uncertainty, and it's good to think about like why would this procedure work? This sounds so simple and dumb. Why would this actually work? And the one way to think about it is the following. So if you model a distribution, you already force the model in some sense to try at least capture the inherent ambiguity in some sense. So this, if at all there is some inherent noise in the label y given x, this will make sure that your model is like kind of correctly specified, and trying to model the stochasticity, you give the model the power to model like a distribution. And when you use ensembles, you're averaging multiple things, and it can, it's not Bayesian model averaging, but it kind of goes after this epistemic uncertainty. What happens if you train the model multiple times and things like this? And the inspiration for ensemble methods is the bootstrap, where the connections between bootstrap and Bayesian inference is better understood in some regimes. And if you train on bootstrap, it has theoretical justification. There's a lot of amazing work done to understand the bootstrap. But in practice, using the entire data set works better. And in fact, there's a striking similarity between these results and what we see in, like, say, ensembles of decision trees, where ensembles were way more popular before. And for instance, like Bremen's random forest used bagging, but later work on extremely randomized trees, it showed that if you can randomize, if you can inject other sources of randomization in your tree construction, you don't really need bagging, and you can train the individual trees on all the data points. And there is work showing that this is my PhD work. Basically, I showed like similar results showing that non-Bayesian ensembles of probabilistic decision trees actually give pretty good uncertainty estimates in practice, which inspired my work with deep nets. So I don't have time to talk about this, but if you all, yeah.
So doesn't this? So how do you say that, you know, like this idea of randomizing the estimator instead of ensembling them? Then why doesn't the Monte Carlo dropout method work?
So I think one way to think about the Monte Carlo dropout, it's kind of like a weak ensemble of sorts, because you're sharing all the components, whereas in my case, I have way more randomization in the individual things. And when you think about from a bias variance trade-off, the samples are more diverse, so the variance reduces. So maybe that could be one way to look at these results. Yeah, so I don't have time to talk about this, but we applied this in like a health application. You can read about the details. So the take-home message that I want to leave home for at least this part is the non-Bayesian probabilistic solutions can be surprisingly effective, and strong non-Bayesian baselines are valuable to understand the limitations of Bayesian methods and how far we can go there. And there's a lot of other promising non-Bayesian solutions that I didn't have time to talk about. One is temperature scaling that I alluded to before, and the methods like Odin and things like that. And combining the two can kind of like give the best of both. So non-Bayesian methods are typically easier to scale. So I think the spirit in which I want to push this work is push whatever can be solved by the non-Bayesian method. Let's use the non-Bayesian methods to do it because it's computationally way easier. And then whatever the Bayesian method is uniquely pushed to do, let's use more sophisticated Bayesian methods to do it. Yeah. And the remaining, how much time do I have? 10 minutes?
Well, yeah, so the class ends at 5:30. We'd like to save like 15 or 20 minutes for questions at the end.
Okay, I'll finish the next part in 10 minutes. I kind of like plan for that. I have a lot of pictures in the second half, so. Okay, so the next part, I'm going to slightly pivot and talk about a different paper. And so this work is some work we started last summer during Eric Nelesnik's internship. And we kind of looked at the out-of-distribution behavior of deep generative models, and I'll just jump into it. So far, I've been only talking about discriminative models, right? So you have like P of y given x, and we are trying to model like the uncertainty around here. And going back to aleatoric, epistemic, and things like this, one of the key things is how do we kind of like distinguish between the two? One of the ingredients we are kind of like missing is you can use generative models, right? Like, so if you model P of x, maybe you can use that to kind of distinguish between the two sources also. So we started looking at this and kind of like models which combine the two. And this goes back to my earlier point that you maybe trust P of y given x. Deep networks are really powerful function approximators, and you can train them to be pretty accurate when x comes from this distribution. But they can be overconfident and wrong when x comes from a different distribution. If we train a generative model, we can use this to reject inputs, right? Like, so this is an old idea proposed by Chris Bishop in this paper, and we wanted to see, okay, how far can we like push this idea? Okay, let's revisit this idea. And the way it kind of like works is the following. So you have your classifier trained on maybe like CFAR or something, and then what you're going to do is at test time, when you see inputs unlike the training data, maybe you have a P of x model which would kind of like reject. So you wouldn't evaluate the model score. You would just output like, I don't know, or say some uniform probability or something. You can use that to decide to reject, right? Like, so this is an idea that's come up a lot of times, and I encourage you to watch this video of the panel discussion at the approximate inference workshop at NeurIPS 2017. And so I think it was probably Max Welling or someone who suggested this idea, and Zubin, following the discussion, he said like you should kind of like build this procedure. You could say a way to detect like novel inputs, and then you should build it into the software. And then Matt Hoffman, who's the moderator, has like, is that hard? And then like Zubin says, if you stick a picture of a chicken into an MNIST classifier, it should be able to say whether it's 7. It should be neither 7 nor a 1, right? Like, so this sounds like an easy enough problem. Can we use P of x models to do it, right? So we decided to try it, and what we did was we took CFAR, and then we trained a generative model to get on CFAR. And we looked at a bunch of generative models where P of x can be computed, and you can use like what's called flows. You can use autoregressive models and VAEs where you cannot really compute P of x, but you can compute a lower bound or log P of x. But we decided to go with flows because it was like simpler. And the setup is the following. So we have trained a generative model, and we are training on CFAR and testing on SVHN. Does the model assign higher likelihoods to CFAR than SVHN? So what do we expect to see? So here's what we saw. So if you train a CFAR model, here's the histogram of log P of x. And you can see that there's a slight gap between train and test, but let's ignore that for now. And we also report bits per dimension, which is the negative log likelihood. So this is the negative of this, basically. And then it assigns 3.3 bits per dimension on average. But if you show it CFAR, shockingly, it assigns way higher likelihood to CFAR than, SVHN than CFAR, even though a human would say SVHN is nothing like the training set, right? Yeah.
So if it assigns higher likelihood to SVHN, do the samples sometimes look like they're from SVHN?
They don't. That's a very interesting discussion as well. I'll come back to that in the very end. Yeah. So it assigns way lower to the bits per dimension. It assigns very way lower bits per dimension, and we are kind of like surprised by this. And there's a big problem, right? If you're trying to use generative models to detect OOD, and generative models themselves can assign way higher likelihoods, what's going on? So is it restricted to flows? So we tested with like pixel CNN, different types of VAEs with like powerful encoders and things like this, and the phenomenon holds the same. And somewhat surprisingly, the phenomenon is also asymmetric with respect to data set. So you may wonder what happens if I train on SVHN and test on CFAR, and there it actually kind of like works as intended, whereas it does fail when you train on CFAR and test on SVHN. And it's not restricted to this pair. It turns out it holds in like many other pairs, and you can see the paper for a lot of other results, fashionableness, temness, Celebi, SVHN, and things like this. So it's not just caused by overfitting to the training data in some sense. You can plot the BPD throughout the course of training, and you can see that it's pretty constant. And we tried some simple things that may fix the robustness to OOD, like ensembles, like I talked about earlier, may help fix the problem. In this case, it didn't actually, at least for our ensembles, it didn't fix this problem. And what's going on? So we decided to dig a bit deeper into flows. In the interest of time, I'll kind of like just skip through and get to the main message. But what we basically looked at was, we looked at a subset of models, of flow-based models, which we call constant volume glow. It has this special property that it allows us to analytically understand like what's going on. You can do some math. And basically what we looked at was, given some model trained on theta, if you evaluate the likelihood under some like a different distribution, when would this be higher than whatever it assigns to the training distribution, right? Like, so we can start with this, and then let's see where it takes us. And if for flow-based model, it turns out, take my word for it, but turns out you can, if you do a Taylor series, if you do a second order expansion of the log likelihood and you compute the expectations, this is what you get. And basically, this is the property of the flow-based model. This happens to be the moments. I've made some assumptions here, but empirically they capture the bigger effect. So I think they're consistent with our message. So for the specific model, because of this term is usually very hard to optimize, but analyze. But if for constant volume glow, this turns out to be quite easy. And with some more math, basically at the end, what we show is that for CFAR and SVHN statistics, if you plug them in, what we see here is that it depends on whether the second moment of the non-training distribution happens to be lower than this one. Basically, if you evaluate on a data set whose intrinsic variance is way lower, it turns out these models tend to assign way higher probabilities. And we empirically evaluated like these variances from the CFAR and SVHN data sets, and they agree with the theory, what the theory would predict. And furthermore, to validate the theory, what we did was, there is an easy way to reduce the variance. You just transform everything into grayscale, and we see whether that checks out as well. And motivated by this, we tried, like, it turns out that for CFAR and SVHN, if you gray them, the likelihood just shoots up like crazy. And this is also consistent. So what's going on? This turns out to be, this also inspires, given that the model has some special properties, it also points us in some directions where we can fix the modeling. And it points us in some helpful directions, which we are kind of working on right now. So the summary of the results is, we showed these, so there are all these class of deep generative models. We showed empirical results for all of these ones. like we pick state-of-the-art examples, and the bits per dimension and everything is close to state-of-the-art. So it's not because the model is not trained enough or anything like that. And then analytical results we can analyze for the subset of models where we can do a lot more theory to really understand like what's going on. We did that. And the take-home message for this part is that deep generative models, there's been a lot of impressive progress on like GANs, VAEs, flows, you name it, autoregressive models, WaveNet, but they have problems with the OOD dataset as well. And using a generative model is not going to automatically give you that kind of like robustness. And for flow-based models, we explained this phenomenon through relative variance. So I showed you like grayscale, but it turns out that if you show constant images, these methods tend to assign way higher likelihoods as well. So even this is a really simple way to, this is non-adversarial also. You don't need to go to great lengths. Even like simple out of distribution can break current classifiers. And the other take-home message is be cautious. You've been using density estimates as kind of like some proxy to similarity score. It's kind of tempting to use P of X as a measure of distance from training data. This goes back to my initial motivation, try and use the P of X. But you should be careful, and this has implications for research around like say novelty search in RL, novelty detection, and anomaly detection and things like this. Yeah, so the papers I spoke about are this one and this one. They're available on my webpage. And we also did some work on combining P of y given x and P of x models, which motivated to find this failure mode. And that paper is also available on my website. And this is a very exciting topic. A lot of interesting work is going on. And we are co-organizing a workshop at ICML with Dan Hendricks and Ishwan, Tom Dietrich, and Justin Gilmer. And I encourage you to attend. And thanks to all of my thanks to you. Thanks to all of my collaborators as well, Alex Pritzel and Charles Blundell, Eric, Aki, Dylan, and EY. And I would like to give a special shout out to Eric, who also prepared fantastic slides which I stole for this talk. Yeah, thank you. Questions? Yeah.
So when you say you train one flow model and one data and test it on a different data, so do you do any engineering in between that, or just test it on?
We just test it. Like, so you take the model output some P of X, and then we just score the model under like a different OOD distribution. Yeah. Someone else had a question?
I actually had a quick question on that map, a couple slides
Okay.
earlier that you presented of deep models. This one, that's no, go forward 2 slides.
Oh, sorry.
In the summary results forward. Yeah, what is that?
Well, it's.
Is there really no overlap between autoregressivity and latent variable models?
Well, I wouldn't read too much. It's basically they are considered broadly to be 2 classes of models. I'm sure, like if you write down, you can make them overlap. Yeah. Yeah, I guess like you could do. Yeah, I wouldn't read too much into the thing. It's more to show like the a different class of models or something. Yeah.
So what's the uncertainty of this map here? Of the decision boundaries in this map?
That's good. I should put error bars.
So do you also include self-supervised models somewhere?
Sorry, what?
So do you include self-supervised models somewhere?
We didn't include them here. So I guess like we mostly investigated models with trained using maximum likelihood, right? Like so because that's a dominant paradigm. We trained like VAEs. We haven't looked at that angle, but maybe that gives you some kind of like robustness. That would be a very interesting line of research to pursue as well. It's more about like the inductive bias of the model rather than the training loss that you use in some sense. So yeah.
So I guess philosophically, why do you think of that, uncertainty where neural networks, like the stuff you're talking about, the first part of your talk, why doesn't everyone use that for every application instead of, just like basically kind of overfitting to a particular test set or whatever?
It's a good question. At least within, I think in a lot of applications, even within DeepMind, like we are pushing for more like taking out these simple methods and trying to add them to like applications. So I didn't talk about it, but one of the applications I mentioned was this healthcare, where we use this application because there you clearly care about like confidence and you want to make sure you're making like the right decisions. There could be tons of other applications as well. I think the main thing is there's really like there weren't a lot of methods which were kind of like model agnostic and really easy to implement, and like simple baselines that maybe are not perfect but get you like 80% of the way on like what a proper Bayesian solution would do. And our method using ensembles, we designed it such that it's simple and really easy to implement on top of like and it seems to get there. And I think more and more people are using it in a lot of applications. And like temperature scaling is also like a great example, right? Like, so all you really need to do is at test time on a validation set, you compute some temperature and you scale the logits, and that's it. So yeah.
Do you think that like the future of the field will really pursue ensemble models, or do you think that like those are relatively too computationally intense and that you're going to find like a better solution that deals with like dropout or randomized data sets?
I think that's a very interesting question. I think sometimes it's useful to have even removing kind of like computational constraints and things like this. If you know that something is possible, it's usually easier to kind of like reverse engineer, figure out like why it actually works. And you ideally want like a really simple method that tacks on. And I think like temperature scaling, for instance, fits the bill, right? Like you're literally learning like one parameter on like a validation set, and really there's no memory overhead or things like that. And there are also different paradigms, right? Like, so people say ensembles are expensive, but maybe given that it's so simple to implement, it's kind of like model agnostic. So if you have a lot of machines, you can actually train ensembles, and then at test time, if you worry about like test time, you can distill the ensemble, which has been very successful, like distillation on its own, and you can do that for it also ends up giving you better uncertainty and things like this, which is like nice to have. So there are different paradigms on like applications. So definitely in cases where you cannot even train like multiple models, more work needs to be done. Yeah, I think like the bootstrap is also something that I think about a lot because it's kind of like so my PhD, I've looked at like ensembles of like decision trees, and there people have actually understood like a lot more of the theory and the mechanics of randomization and how it precisely impacts like trees and things like this. The theory of neural nets is still, there's some results, very exciting results now, but it's still not there. And I hope like as we understand it a bit more, we'll get more efficient ensembles or better ways to randomize neural nets and things like this. So yeah, it took, to be fair, random forests were done, I don't know, like early 2000 or late 90s, and the theory was only done maybe like 15 years after that. So yeah. Any other questions? Yeah, so I think you asked a question about like why do we see like samples? Why do we see like SVHN samples and things like this? So that's actually a very interesting point. It goes back to this notion of like typical sets. So in like high dimension, it could be a phenomenon just to do with like high dimensional spaces. So what happens is if you sample from a high dimensional Gaussian, you almost always end up sampling from near like the surface of the sphere, but the mass, the highest likelihood is actually at the origin. So there's a discrepancy between like samples and where the mass has high density. So this points to like an interesting failure mode. Like just by looking at samples, it's not it's kind of like known. If you read like maybe a note on evaluation of generative models paper, they talk about like the discrepancy between like likelihood and visual samples and things like this. But this may not be something that you see just by sampling from the model. It does not tell you where the model actually puts the biggest mass. Yeah.
So you said with a different data set, the likelihood becomes more, right?
Yeah.
So how about you put an SVHN data set to the flow and get the noise space and get the same like back to the original space? Do you have any image of that to like visually compare how that looks?
For flow-based models, it's perfectly invertible. So for VAEs, we haven't looked at that yet, but it does not properly reconstruct that in that case. Yeah. But for flow-based models, we have looked at a lot of analysis of, so it kind of does this phenomenon, which is also pretty consistent with the theory. It ends up, I don't have it here, but we looked at like the norms of the codes that you get for CFAR and SVHN, and we did like a lot of analysis. And what this is what we actually plugged in here. Like this place, it says you need to plug in like the variance and the, well, not here, but in some other analysis. It's consistent with this as well. So what happens is it ends up projecting the things closer to the origin of the Gaussian, which is why, so the norms are very different. So that's why it assigns a higher likelihood. Yeah.
So do you have some intuition for why it's enough to just do the averaging? Or like, are there situations where you think averaging, or sorry, by averaging I just mean this model, I guess not Bayesian model averaging, but this combination. Like, do you have intuition about like why this is good enough, or like when this is good enough? Are there situations when you should expect it to not work?
Yeah. So I used to have this intuitive mental picture. I don't know if this is actually true, but you can imagine if you have like a multimodal posterior, the like variational approximations kind of go after like one mode and try to model the uncertainty around that mode, right? Like, so if you have like a multimodal posterior, variational approximations are trying to approximate the local uncertainty around a particular mode, because you take the point that you converge against, you estimate maybe like fit a Gaussian or something, which is unimodal. Whereas ensembles kind of put delta masses on multiple modes. So this may be more in the spirit of, these are closer to MCMC in that sense of the intrinsic randomization, that if you there is a lot of theory which studies that under what conditions does SGD converge to SGD performs approximate Bayesian inference. So if you imagine, if you piece together that, you can, under some conditions, you can maybe show that the trajectory of SGD is kind of like performing MCMC, and it samples from multiple modes, and ensembles are kind of doing something similar in that sense. But it's more work needs to be done to precisely write this down and study this in proper, like properly understand like what's going on. Yeah. But in trees, for instance, people have studied like in terms of like bias variance trade-off. You can explicitly write down like the bias of an individual tree, and you can see that it's very high variance, so you need some averaging to do it. But these kind of things are, these kind of studies are still missing for deep neural nets. Yeah. That'd be interesting to, that'd be a very interesting angle to pursue.
Yeah. So I guess you talked about these two types of uncertainty, epistemic and aleatoric uncertainty. I've seen other types of uncertainty discussed as well. So like one example might just be that the true model doesn't actually lie within your model family.
Yeah.
And so I don't know what we would call that. I guess I would call it like specification of uncertainty. I don't know, is there maybe there's a better name for it. But it seems like that's another thing that you might want to care about. Yeah,
that's true. Yeah, I only spoke about, in the context of deep nets, if you appeal to the universal approximation and things like this, you may kind of like say that is the case, but I think that's a great point. I don't know if there is a name for it, but I guess they just call like the risk of misspecified models and things like this. People have studied this for other class of models. And one of the interesting things is that if you use a misspecified model, it turns out that bootstrap or ensemble-based methods tend to be, their risk is actually lower than Bayesian procedure. So they're kind of like more robust to violations of model misspecification and things like this. So
sorry, which things are more robust?
Bootstrap is more robust. tends to be more robust because it makes fewer assumptions about like how precisely it's basically Bayesian inference assumes that the likelihood and prior are correctly specified and tries to compute the posterior. Bootstrap makes less strong assumptions on both of them holding. It's somewhat more agnostic. So even if you're misspecified, it turns out to have like lower risk. Yeah, but that is actually very hard to analyze because in some sense it does feels like a much harder problem than any of these two in some sense. Yeah.
Yeah. I mean, even in the bootstrap, the thing I'd be worried about is that as n goes to infinity,
yeah,
the epistemic uncertainty is going to go to 0.
Yeah.
But the misspecification uncertainty is still going to lie around, and in general, like, means that your like confidence interval, or like sort of like the uncertainty in your predictions should probably be higher than just what your model
yeah.
is saying. And it seems like Bootstrap is always going to have sort of always going to converge to a single model as n goes to infinity.
So actually, Bootstrap wouldn't converge, right? Like because everything is trained on a different data set. So Bootstrap is more robust in that sense. Bayesian model averaging would peak at a single model, but Bootstrap would still maybe in the really far end limit where it removes all kinds. It cover the entire input space. They may all converge to the same space, but since you're training on a Bootstrap sample, each one sees maybe only like the number of unique data points in a Bootstrap sample is maybe like 2/3 or something, 63% or something. So it still sees fewer examples, so it may overfit less on. They may be somewhat more different in that sense. Yeah.
How do, regarding to appealing to universal approximation, what about, so that, I mean, that of course assumes like an infinitely wide network. What about, like, how would you be able to do that with a finite parameter space, like an actual?
Yeah. I think I just meant like with neural nets you can make the width arbitrary enough to, if this was a serious issue, you could make the width as wide as possible so that some notion of universality kicks in for practical purposes. But if you're, it's not a, I just meant it to show that the impact that model misspecification may not be the biggest problem with neural nets. So it's unclear whether that's the, so there are three sources. One is, even if you, what I was trying to say was, even assuming that the model is correctly specified, we don't have a good handle on how do you decompose these two sources of uncertainty and things like this. I see model misspecification and the understanding the effect of that as slightly lower priority than these two in some sense.
Well,
but it's possible that they're all intertwined.
I mean, yeah, like state-of-the-art neural networks, they are infinitely wide, and like people will come up like basically say, okay, like this inductive bias or whatever, it's like I've got an intuition, I don't know, adding residual connections is good or something, for example, and then performance is boosted. But these are all, of course, like any practical neural network is going to not be infinitely wide. I mean, like this is what I'm saying. Is like even the state-of-the-art stuff is, I guess I'm just saying I don't 100% agree that it's lower priority because it's never going to be the case that we have a
sure
perfect. Yeah, sure. I don't know.
Yeah.
But who knows?
I meant that in the sense of, given that we've been able to use neural nets as very good function approximators for accuracy, I see that as some kind of like indicator that if model misspecification were truly the issue, maybe it would be somewhat reflected in lower accuracy or other things or something like that. The fact that they are able to really do very good function approximation, if you think about like the multiple terms in decomposing the bias variance trade-off and things like this, it does feel like, at least if you take this as some evidence that model misspecification may not be the biggest issue. But it's possible that this is actually caused by the model becoming overfitting in some other weird sense or something. Yeah, I don't know the answer. Yeah.
All right. It's 5:30, so we should call it a day. So let's all thank you.
Thank you.